Acid-base titration. This is what we're doing in lab today. It's a way to quantify the amount of acid or base in a solution. And it uses solution stoichiometry, which we just finished talking about in Chapter 13. So what we do in titration is we take a solution with a known concentration and we react it with a solution that has an unknown concentration. And based on the amounts of each that we need, we can figure out what the unknown concentration is. So we'll have some illustrations here. So if we have hydrochloric acid, we're going to represent hydrochloric acid as just hydrogen ions because I knew there was a reason that this was here. This is the net ionic equation. Hydrogen ion plus hydroxide ion goes to water. If we're reacting hydrochloric acid and sodium hydroxide, what happens to the chloride ions? They're just still there, right? It's like the spectators that go to a boxing match. They come out, they look exactly the same as before. The boxers that were in the fight are all beat up, right? The spectators are unchanged. So sodium is a spectator. It doesn't show up in the net ionic equation, which shows the people that were actually in the boxing ring fighting with each other. And in hydrochloric acid, the chlorine doesn't participate in anything. It's just hanging out. So we're going to illustrate hydrochloric acid as just being the hydrogen ions because the chloride ions really don't matter. They are there, but we're not drawing them for simplicity. So here is an illustration of a titration. This is a burette, and in the burette is sodium hydroxide. We're not drawing the sodium ions because they're just hanging out and they make the drawing confusing. So this is hydroxide, these little red and white, one oxygen, one hydrogen. So we've got hydroxide here, and we have hydrochloric acid in our flask. As we add hydroxide to the flask, the hydroxide ion reacts with a hydrogen ion and forms a water molecule. And as these hydroxide ions come into this solution, they take out the hydrogens. They react with them. Does that make sense? Eventually, we'll get to the point where we've added an equal number of hydroxide ions to a number of them equal to the number of hydrogen ions that were initially in the beaker. That's a stoichiometric amount. We've got them matched up just right. And that's what we call the equivalence point, because the amount of hydroxide is equal to the amount of hydrogen ion. We have a complete reaction. So the moles of hydroxide is equal to the moles of hydrogen ion in the sample, and the titration is complete. Now the trick, of course, is how do you know when you've done that? Well, we use what's called an indicator because it indicates the end of the reaction. Indicators are dyes that change colors based on the acidity of the solution that they're in. And the one we're going to use today is phenolphthalein. So what we do is we carefully measure the volume of each solution, and we know the concentration of one of them, we know the volume of both, and then we can calculate the concentration that we don't know. So here's the same idea, but with photographs. So here we've got an Erlenmeyer flask containing a hydrochloric acid solution that contains a small amount of the indicator phenolphthalein. It's a kind of a funny word, phenolphthalein. That second pH is kind of silent. So phenolphthalein. There's sodium hydroxide in the burette. Both of these solutions are colorless. They look like water. So it kind of looks like magic when this happens. As we add the sodium hydroxide, it begins to react with the hydrogen ions in the solution. The reason we see a little pink here is when the sodium hydroxide first drops in here, it's more concentrated and it hasn't spread out and reacted with hydrogen yet. And so what we do is we swirl the flask to mix it. And that's one of the reasons that we use a flask like this instead of a beaker, is it's really hard to splash it out of an Erlenmeyer flask. Whereas if you were using a beaker, it's much easier to splash, and you want everything to stay in the flask. So what's going to happen is we'll keep adding sodium hydroxide. You have to be patient. Okay, you just got to be patient. Keep adding sodium hydroxide, and as you do, you'll see that this temporary pink color persists longer and longer. That tells you you're getting closer. Be careful, slow down. Ideally, what will happen is you can add 1 drop and swirl it. It might stay pink for a few seconds, but then it'll go away and be clear again. Then you add 1 more drop and you swirl it some more, and you'll get this light pink color that will last for around 15 to 30 seconds. Eventually, it will go away. And I'll show you, I'll give you a little demonstration in class of how we can make the pink color go away. It reacts with carbon dioxide that's in the air and dissolves into the solution, and that neutralizes the sodium hydroxide. The reason this turns pink is because we've gone a teeny tiny bit past the end point. There's no way around that. But we don't want to go way past the end point. If we go, 5 drops or a milliliter past the end point, you're not going to have pale pink. You're going to have this fuchsia color. That's one of my favorite colors. You wore phenolphthalein pink today. Good for you. I love that color. But that's not what we want to see in our flasks. We want to see pale pink, blush pink. So let's do an example of a calculation, and you'll need to do a calculation like this for lab today. So the titration, which is just a technique, of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What's the concentration of the unknown H2SO4 solution? We need a balanced chemical equation. The best technique, the technique that produces the best long-term results for solving titration problems, is to use solution stoichiometry. There are other shortcut ways that work for some situations, but I think it's really best to think of it in terms of solution stoichiometry. So we need the equation. So we've got sulfuric acid, and I'm going to do this kind of quickly because we've already covered how we do this, and potassium hydroxide. We're mixing those. And what are the products of an acid-base neutralization? Water and salt. Right? So we're going to get water and salt. The H2 from the acid, the hydrogens, and the OH from the base are what go into the water. And so what we're going to have left is potassium and sulfate. So potassium is a +1 ion. Sulfate is a 2- ion. So the formula for that is K2SO4. We need to make sure the equation is balanced. I kind of skipped over this in the last example by accident. This acid has 2 hydrogens. We call that a diprotic acid because it has 2 hydrogens. Why don't we call it a dihydrogen acid? Well, let's think about a hydrogen atom. How many protons does it have? 1. How many electrons? 1. When you make a hydrogen ion, it still has 1 proton, but you took its electron away, right? So what's left? Just a proton. A hydrogen ion is just a proton. Kind of crazy to think about. So we call this a diprotic acid because it has 2 hydrogen ions, 2 protons. There are triprotic acids like H3PO4. There are a lot of monoprotic acids like HCl and HI. We can actually look at that, and that helps us predict balancing this equation. If this is a diprotic acid, it's going to produce 2 moles of hydrogen. 2 moles of water. And we're going to need 2 moles of the base, of a base like this. And we can look at this and we see 2 potassiums. Yeah, we need 2 potassium hydroxides. 2 hydrogens here combined with the 2 hydroxides make the 2 water molecules. I'm going to erase all this junk down here because I need the space for the calculation. So you have to start with the balanced chemical equation. Now we're going to do what we've done before. We're going to take these numbers and we're going to write them down here. 20 milliliters of H2SO4. So I'm going to write 20.0 milliliters under H2SO4. 22.87 milliliters of KOH. So under KOH, 22.87 milliliters. And here's a concentration, 0.158. What's the capital M mean? Molarity, moles per liter. So we're going to write it down that way. 0.158 moles per liter. We want to find the concentration. Chemists generally use molarity, so we're going to assume that molarity will be acceptable here. Molarity is moles per liter, right? Let's write this up in the top. Molarity, capital M, is moles per liter. So then we need to think about a path. How are we going to get to where we need to go? We have 2 volumes here and 1 concentration. And so what I told you in the past, where you just look at the units and say, well, this is a per unit, that's going to be a conversion factor, that's true. But now I have 2 volumes with just milliliters. How do I know which one to start with? Well, let's think about stoichiometry. We did, our standard thing was grams to moles to grams. And with solution stoichiometry, we said that we could also start with a volume in liters and end up with a volume in liters. Liters to moles to moles to liters. Well, that doesn't help us a lot because we've got 2 volumes. But which of these compounds are we trying to learn something about? The H2SO4. We're trying to find question mark moles per liter. So do we want to start with that one? The thing we're trying to figure out about? Or should we start with this one and then calculate that one? We're going to start with the KOH. So we'll go with liters of KOH to moles of KOH, because we've got the molarity here. From moles of KOH to moles of sulfuric acid. But then we don't want either of these, do we? We want molarity. Well, if we found moles, how could we get moles per liter? Do we know the volume? We do. If we find the moles, could we just divide by the volume in liters? Yeah, that would work really well, actually. Okay. Now, this says liters. And these are in milliliters. So there's different ways to approach this. We can convert those to liters first, or we can stick them in there as milliliters and say, we'll take care of that later. Which one do you want to do? Convert to liters? Okay. So, converting to liters, that's not what I wanted to do. I don't want to do that either. Oh, please come back to me. I hate it when I do stuff like that. I think I lost everything I just wrote. Darn it. Pause. We'll call that good enough. We're going to convert to liters. Taking milliliters to liters, hopefully you've become comfortable with that by now. I don't have space to write all that out. You would take the milliliters and multiply by 10 to the minus third liters per milliliter. Or you recognize that milliliters are smaller than liters by a factor of 1,000 and that we need to move the decimal point over 3 places. So this is going to be 0.0200 liters. Oh, I didn't leave nearly enough space. And 22.87 is going to equal 0.02287 liters. So if you need to write it all out, please do that. I don't have space here. So I've converted these to liters. So now we're ready to go. We're going to start with the volume of the KOH, liters of KOH. And I accidentally erased our path. We're going liters to moles. Moles of KOH per liter of KOH. And then from moles of KOH to moles of H2SO4. So those canceled. We want moles of KOH to cancel. And at that point, what have we calculated? What units left? Moles of H2SO4. What do we need to do to that to turn it into a molarity, moles per liter? Divide by the volume. So here, to divide by something, we're going to multiply by 1 over. The volume is 0.02. 0.0200 liters. This unit's not canceling out. That unit's not canceling out. This is a little twist on the end. Not technically dimensional analysis, where we're just converting units. And if you want to see a slightly different way, you can watch the Tulare version of this section, and I did it a little differently there. So this conversion factor, moles per liter, is the concentration that we were given, 0.158. This relationship between moles of acid and moles of base comes from where? The equation. 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide. So we've got 1 to 2. Now we've got all of our units and our numbers in there, and we can calculate 0.02287 times 0.158 divided by 2 divided by 0.02 equals. And this will equal, let's see, here we have 3 sig figs and 4 and 3. So we should round this to 3, 0.0903 moles per liter, or capital M. Any questions?